I thought I'd put together a kind of synthesis video of what we've tried to teach over the last 5 tutorial sessions in trying to evaluate enhanced irrigation devices in an in vivo environment. If you followed these tutorials, putting all this together may help you crystallize some of these ideas and make your image interpretation task a little easier. I'll try to combine pictorial representations with some recent scientific advances and relate those things to the actual SEM clinical work we are doing at PERF. When you look at SEM images of dentin and pulp, you are confronted with an overwhelming array of confusing images and patterns that can be very puzzling, if not disconcerting. The trick is to develop some understanding of the anatomy along with a basic understanding of the mineralization process in dentin, as well as some familiarity with specimen preparation issues and the artifacts they can produce. The first step is to understand the orientation of the specimen in relationship to the detector that you're using. For example, we are typically looking at the axial dentinal wall after instrumentation and irrigation. What comprises that axial wall? If you look at this H&E histological picture, you don't get a good sense of the complexity that you're actually confronted with. Historically, endodontists have referred to the organic and inorganic pulpal material outlined by all the tissues within the red box as the smear layer, all the tissues compressed by instrumentation and irrigation procedures, as well as debris from the instrumentation itself, all referred to as smear because in SEM pictures it looks smeared or lacking in discernible features, as these images show. What is missed in this explanation, as this SEM tries to demonstrate, is that the tissues that comprise the predentin itself is contained within this layer. So a closer examination of what exactly constitutes the elements within the predentin is in order. So the smear layer appears as a kind of covering over the dentinal tubules. The dentinal tubular layer, which we call the mineralization front, because it contains the fully mineralized dentin and the tome's processes. But what is often unappreciated is that it also contains all the elements in the predentin. Let's do a thought experiment and imagine we could stand and observe an unfixed specimen right at the predentin border, looking toward the mineralization front. What would we see? From your observational vantage point, when you see the tubules like you do on the right, you have to assume all of the smear layer and the constituents of the predentin are missing from this picture. And in this picture, the predentin tissues are also missing, and the image is easy, therefore, to interpret. But what would the picture look like if they weren't missing? When this predentin layer is not missing, you have to deal with how does a tissue appear when it has partial nucleation of hydroxyapatite crystals interspersed throughout in various stages of mineralization. So you have to ask, what does this tissue look like from your vantage point looking toward the mineralization front? What complicates the picture is the predentin area, because that area is partially mineralized and contains not only collagen forming the substructure of the tubule, but also a host of non collagenous proteins that actually control the mineralization process itself. It is this area that creates the confusing SEM picture. To answer the question of what we would see from our vantage point, we have to ask, what do we actually know about predentin tissue? Well, we know from earlier tutorials in our series that the nucleation events resulting in the mineralization of the predentin happen in a gradated series of events controlled by non-collagenous proteins secreted by the odontoblast. We know there are 3 theories of dentin mineralization, and that probably all 3 theories operate here, perhaps in the 3 areas I have outlined here. The classical ordered cluster theory in Area 1, the non-classical amorphous mineral clusters theory in Area 2, and the gel liquid theory in Area 3, where the final mineralization takes place. These three theories probably operate at different areas within the predentin complex. Recent research has shed some light on the process of mineralization, taking calcium phosphate ions to the final hydroxyapatite crystals. It is a stepwise, gradated process using supersaturated solutions of calcium phosphate, which we refer to as amorphous calcium phosphate. And the actual nucleation events are thermodynamically controlled by non-collagenous proteins secreted by the odontoblast. The stepwise growth of hydroxyapatite crystals from supersaturated gel that surrounds the collagen fibrils is important to understand because given our vantage point at the predentin border, we are observing all those different steps at one point in time, thus the confusing picture. The theories advanced for this control process, as reviewed in our biomineralization tutorial, postulate a supersaturation of amorphous hydroxyapatite in a gel-like environment. And as you get closer to the final mineralization border, certain inherently disordered proteins control the last stages of mineralization. So if you can imagine looking into a jelly-like material with many growing seeds in it, it might be easier to picture. If we go back to our TEM image of the predentin zone, standing at our vantage point, the nucleation we see will be scattered and non-uniform as you look into the mineralizing predentin. Pictorially, if you envision intrinsically disordered proteins controlling the steps in these events, as this diagram shows, it might be easier to conceptuate how this process occurs. Using immunochemistry analysis, these inherently disordered proteins secreted by the odontoblast have been clearly demonstrated. So now when you see this picture of globular dentin, you should understand the globular nature of it is due to what is missing and that you can't see. All the disordered proteoglycan and glycosaminoglycans that fill these spaces, but have been removed by the dehydration and specimen preparation processing. And incremental crystal growth in plate-like arrangements as nucleation proceeds hopefully will give SEM structures like this more meaning to you as you understand what is actually happening. Now, when we zoom into areas, the actual structure of the predentin and the effects of the dehydration and precipitation of the predentin proteins gives you more context in what these structures represent. I hope this clumsy attempt to put some of these issues in clearer context will help you as you grow your pattern recognition skills in SEM interpretation.